Okay, so Friday you did work on project day. So today we will continue into chapter 17. So let's talk first about what the syllabus says is happening this week. Leanna asked me about this a minute ago. If you're following the syllabus, it says Friday we have a test. Well, that's not going to happen this Friday, but we have this week and then 2 more weeks of classes. All right? So the test will probably be exactly 1 week later than what the syllabus says. Yeah. I could actually, well, actually, it'll probably be Wednesday. It'll probably be, next Wednesday, so a week and a half away. Because I don't think I want to wait until that Friday to do it. So we'll finish chapter 17 this week. Probably review for the exam on Monday. What's the date on Monday?
Monday's the 25th.
25th. Okay. And then on Wednesday we'll take the test, so that'd be the 27th. Right? So April 27th will be your 3rd exam. And it will cover the analysis of covariance, supplement. No, we already covered that. We did that on the last test because we delayed the last test. So it'll be chapters 14, 15, and 17. 14 was logistic regression, 15 is non-parametric tests, and then 17 is what we're doing right now, quality control stuff. Okay, so chapter 17, quality control. What I want to talk about today is control charts. And so I've got an example, and we're going to start introducing SAS, using SAS to do some of this stuff today. Does anybody have any questions before I get going on what we've talked about so far? All we've done so far in chapter 17 was a bunch of terminology.
Yeah.
So I did what a process was and what, yeah, all that. Any questions over that stuff? Oh, here's mine. Where did I lay my book? So, if there's no questions, let's talk about what we mean by a control chart. All of those things that we talked about last time, I'm not going to spend a lot of class time and not a lot of homework time for you in terms of that stuff. That's at more of a higher level, where if you were on an actual team in a company, you would be the statistician on the team maybe, and the rest of them would be the ones that were experts in the process and what could go wrong and all that. So you'd be there more to kind of lead them in the direction, well, think about variability. What could cause variability? Right? So in terms of a manufacturing process, variability is your enemy. Right? What do I mean by that?
Things being different.
When things are different, that means some are good, some are bad. Right? The tighter you can keep things, the tighter you can keep the variability, the less variability you have, the more similar all the project or all the outputs are.
Tolerance.
And so, yeah, the tolerance is much tighter, and so customers are more happy, right? If they buy ball bearings from you, they expect the ball bearings to be a certain diameter, so they'll fit in their machine or whatever. Well, if there's too much variability, then some of them aren't useful. Some of them will cause problems, but tight variability is good. So part of control charts is to determine the difference between what we call common cause variation and special cause. So quotes around that: common cause variation and special cause. So using your intuition, what do you suppose we mean by common cause variation?
Like standard, like normal stuff that happens.
Yeah, exactly. Normal stuff that's going to happen day to day that you really can't control. Right? So, just one example is like a process that you want to control is how long does it take our telemarketing, or let's do help desk, right? You got people sitting at a help desk waiting for people to call and ask for help on software, whatever, right? So the process you want to control is how long it takes to give them a response, right? So what are some common cause variation that you can think of? Why would somebody's response take longer than another person's response?
Experience.
Experience of what?
In the job.
So you're talking about experience for the person who's on the help desk, right? So I wouldn't call that common cause variation. I'd call that special cause, right?
Like how fast they talk.
Okay. It might take longer to respond. So even if the same person on the receiving end of the call, think about things that could be different about the call coming in. So if the person on the call, the person that's calling you stammers and has trouble getting their point across, and well, I'm looking at the screen, and that could affect, and you can't control that, right? So that would be common cause variation. So that's a good example. How difficult their particular problem is something you can't control. So things that you can't control would be common cause variation, and that's right. But what you said, the experience of the person answering the call could affect how long it takes to respond, definitely. But that's something.
That either.
Well, you can.
Well,
Right?
if they're brand new, they can't.
Right, but what can you do to try to limit that variation? If you have somebody who's brand new on the job, they don't have any experience, that's going to cause what we call a disturbance in the process. All of a sudden, boy, if the call goes to Bill, then my time shoots up, right? So can you think of anything you could do for Bill to keep his time shorter? Okay, he listens in, he job shadows, and learns the process. You give him experience without it affecting a true customer. You give him lots of practice things. Hey, go call Bill. Things like that. So that's special cause. Those are things you can't affect. Right? So the idea of a control chart is to try to separate out what's common cause and what's special cause, right? And a lot of times special cause are what we call disturbances. Something happened, right? They dropped a monkey wrench into the machine, and all of a sudden the products are coming out bad, so things get out of whack. So what we want to talk about, or what we want to look at, is determine the pattern over time. And so I'll talk about measurements, the pattern of measurements. So whatever it is that you're measuring about your process. So the one I was just describing was the response time in a call center. Well, you're measuring time. Ball bearings, you're measuring the diameter of the ball bearing. So whatever it is you're measuring, determine the pattern of measurements over time. If it appears stable, and the results are acceptable, and by acceptable you usually are thinking in terms of your customers. If your customers are happy with your product, your variation looks to be stable over time. It's not getting bigger, it's not, fluctuating wildly, then the results are acceptable. then the process is said to be in control. Okay. So the whole setup of quality control statistics has different phases that you go through. And in the first stage or phase, you're just plotting this pattern of measurements over time. What is our process? What is our amount of variability? What is our mean? Right? So, and then once you determine, okay, this is, quote, in control, then you go into the process monitoring phase, and you start to track it over time, and you have triggers set up so that if some special cause occurs and it shoots up, goes above some limit, then it sounds an alarm. Basically, you're alerted, and maybe just the statistician runs down the hall and goes, whoa, you're out of control. But somehow you get alerted that, hey, we need to stop the thing, or we need to fix something with our process. Okay? So stage one, I just described, is the setup stage. So you establish what is in control, what's meant by in control. You're going to gather past data. And if you don't have past data, then you just have to realize that, well, it's going to take me a while to get my quality control process set up. So during the setup stage, you may be gathering, this says past data. You get data from the past as much as you have. But if you don't have enough, then you've got to monitor for a while, gather past or future data. To understand the normal behavior of the process. And remember, we're monitoring some particular measurement. So what is the normal pattern of variability in that particular measurement? We need to understand what we mean by normal, or what we mean by in control. So we're going to gather data, either past or future data, to establish that. We're going to estimate from that past data, or the data that we collect, estimate mu and sigma. So what's mu? The average of that particular measurement across time. So it's the population mean. So if you're filling tubes of toothpaste and you're supposed to put so many ounces in each tube, not every tube is going to have exactly the same amount. So what's the mean? The mean should be, well, actually, what do you think the mean should be? Let's say you got, I don't even know what a tube of toothpaste weighs, 6-ounce tube of toothpaste. What would the target fill capacity be? What would you want the mean to be? Yeah, that's what most people would say, 6 ounces. A little over 6. You would actually want the mean to be a little over 6. And why? Well, because of our old friend, the normal distribution, right? So if the fill rate, if it's a 6-ounce tube, and I set it at 6, I set my machine so that my population mean is 6, then what percent of tubes do you put out on the market that are underfilled? 50% of them. Half the tubes out there don't have enough toothpaste in them. Right? But if you set this at, say, 6.1, and you keep your variability small enough, then maybe 6 is right there, then you only have, say, 2.5% are underfilled. And a lot of times it's a regulatory thing, right? I don't know how much the U.S. government gets involved with toothpaste, but in my world, in the pharmaceutical industry, they pay a lot of attention to your amount of active ingredient, right? So they want very small percentages of the tubes of toothpaste to be underfilled. So you set your target a little bit high. Well, so you have a target idea for this mu. Then you collected this past and possibly some future data to determine, well, what is mu? And then you see how it matches up with what your target is to know if you're where you need to be. All right? And then sigma is the variability. How spread out is this distribution? So obviously, if I'm filling tubes of toothpaste and I have a lot of variability, that's bad. Some tubes have 8 ounces in them, some only have 4 in them. You'd have a lot of unhappy customers, and you'd have some unhappy management because, you mean you're only charging them for 6 ounces, but you gave them 8? So you want to control that variability too.
Somebody did this with Taco Bell. How much meat is in your meat product? And they did a random sample against Taco Bell, and they came up short on the amount of meat, their protein that was supposed to be in their meat
The amount
product.
of protein.
Yeah, the amount of
Okay.
protein, the amount of real meat that was actually in there. I don't think they call meat what we would think of as meat, but protein. But yeah, there was meat there that was supposed to be in their meat product, and they came up short on that. And they said, no. On a larger sample, we guarantee that we fit exactly what we're supposed to do by standards and stuff.
Yeah,
It's slick.
and that's an excellent example of a process with low quality. I mean, there's a lot of chances for common cause variation, right? You got a high school kid back there with a spoon and he's flipping meat onto a tortilla, right? There's a lot of chance for variability there. So if you want to really make it tight, if it mattered, then you'd have to get a better device than that spoon to measure it and do a lot of training and try to control those kind of things. You want to keep that variability small. So sigma is your estimate of variability, and you need estimates of both the mean and the variability. Right? So then, once you have that, you have those estimates, then you take, then the second thing that I don't know if I put oh yeah, I called it stage 1, so let me erase that and call this stage 2 instead of just 2. Stage 2 is process monitoring. So after you've figured out, well, what is meant by in control, now you continue monitoring into the future to see that you stay in control. So we typically assume that X, whatever your measurement is, call it X. X has a constant distribution. It doesn't say normal, but typically we assume a normal distribution. But anyway, it's got to be constant, the same distribution over time. A constant distribution usually will assume normal. And then it has been operating sufficiently long. I'll just say long enough to understand its mean and standard deviation. Okay. Been operating long enough to understand its mean and standard deviation. So now, once we start monitoring the process, the way we do that, we start with a small sample. And very typical, we use n equal 4 or 5 in our sample. And those are consecutive measurements. So consecutive measurements doesn't sound very random, but we actually need that assumption. Those readings have to be close enough together that you assume the process is stable during the time that you drew those 4 or 5 observations. So that's important. So I'll say important. These 4 or 5 readings are close enough in time to assume a stable process for at least that long. Right? Assume a stable process. So then what we'll do with those samples, over time we'll draw these small samples, 4 or 5 observations, and we'll draw one on, today, on Monday, and then maybe draw another one on Thursday, and then another one the next Tuesday or whatever. And so we're looking at a control chart of those sample means, not the 4 or 5 in a sample, how they vary. Right? We're assuming that, well, within those 4 or 5, it was stable. So over time, now, is it staying stable? That's what we're looking at. So if you can assume that it's in control, if in control, the same sigma describes the standard deviation for any time period. Describes okay? So, the steps of process monitoring. Once we've gone through those 2 stages, so that we understand what we mean by in control, we've got a good estimate of mu and a good estimate of sigma, then we take samples of size n at regular intervals. And those samples are samples of 4 or 5 I was talking about. Take, I need the word samples. Take samples 4 or 5 at regular intervals. And then plot the x bars against time. When I say against, what does that mean? That's the x-axis. So time is the x-axis. Right? So time is down here. And it doesn't have to be necessarily like calendar time or chronological time. It's just order. This is the first one, this is the second one, this is the third one. So 1, 2, 3. But the assumption here is they're at regular intervals. Right? So you can't take one this week, one next week, wait 6 months, take another one. Because a lot could happen in 6 months and the thing could be out of control. You have to be able to assume that the same distribution is describing the x bar each time. Okay, so you might get a dot here and a dot there, and over time. So this is called an X bar chart. So on that X bar chart, you draw a horizontal line. Well, I was going to switch colors, but make it fancy. You draw a horizontal line at your estimate of what mu is. Now remember, by this point, you've estimated mu using past data. So you're pretty sure, yeah, that's our population mean. Right? Now you're drawing regular interval samples and plotting them, and you want to see that they meander around that line, but not too far away from that line. So how far is too far away from that line? Remember our old friend, the empirical rule? All or nearly all sample means should be how many standard errors away from that line? 3. All or nearly all, right? 95% should be within 2, but 99.7% should be within 3. So that's the typical thing to do, is to draw another dotted line above and below, and then these two lines will be at mu plus and minus 3. I'm going to run out of room here, but let's see if I can squeeze this in. 3 sigma over square root of n. Can you read that? So remember, we've estimated sigma. This is not the sigma from a particular sample of size 4 or 5. This is the sigma of the whole population that we estimated from a lot of past data. Right? So sigma over the square root of n, that is your 4 or 5, that each x bar is taken from a sample of that size. Right? So n is 4 or 5 or 6, 7, whatever, but usually they use a 4 or 5. 3 of those give you the upper limit and the lower limit of what they consider in control. So we're used to UCL standing for upper confidence limit. It's sort of the same idea. So you can think of it as upper control limit, lower control limit. So as long as you're staying inside those dotted lines, you're saying, okay, that's just common cause variation, that's what I expect to see, and hopefully these two limits, the upper limit and the lower limit, are still within what the customer would consider acceptable. If it's not, if you make this calculation, you estimate sigma, you estimate mu, then you take 3 times the standard error, and you draw these lines, but you got tubes of toothpaste that are, way beyond what the customer would accept. This was 4 and this is 8. Then, what do you suppose, as a manufacturer, your next step would be? Get new equipment. Figure out, well, something's wrong with my process, right? Something's wrong with the process. I've got quality control steps in here. Something's wrong with the thing that fills it, and so I need a better machine, or I need something. So if you go to this trouble, but these aren't acceptable, then you're not really ready to monitor and stay in control, because you'd have to say, well, that's not really in control. Right? So there may be a fair amount of time that goes by before you get a process that is acceptable. Yeah.
Well, if you're getting like 4 and 8, wouldn't that mean that all the past data that you got your standard deviation is way off?
Yeah, and what it means is that your past data is too variable. You've got too much variation in this process. So you need to go back, do your flow chart, do your herringbone chart, those things, figure out, well, what is causing all this extra variability. Get rid of the special causes of variability that you can, so that nothing but small amounts of common cause variation are left, and then recollect data for a long enough period of time, re-estimate until you get those limits that are acceptable outputs. So we're assuming that's all been done before you really are in process monitoring, which is what the steps were given here. Okay, so I started writing step number 1. You do this. Step number 2 is to draw that center line. Right? So that's called the center line. And then step number 3 is to draw the limits lines. Yeah, that's pretty. Got a curvy arrow. Step number 3 is get the upper and lower limits. Okay, so then if you're going along and you get a point that falls outside of the limit, and you think, okay, something's wrong, you mark that one, and they literally say this in the book, is marked with an X to show, well, I don't know. I don't know if you would actually do that, but if you're putting it on paper and you're handing it to your manager or the foreman of the plant or whatever, then you want to show, okay, this point's a problem. This point's a problem. And when a problem is identified, there may be some reason. And a lot of times the non-statistical people on the team will say, oh, that's the day we hired Bill. So Bill got in there and shot our mean up. Well, that's a special cause. That's a disturbance in the process. So anything that's part of the team function in quality control is to, when the control chart flags a problem, see if you can figure out why. Maybe you can't. Maybe, well, it's just one of those 0.3% of the time that it goes out just by random chance. You take another sample and it's back in, then you don't worry too much about it. But if things start to drift, that's when you really have a problem. Right? Or you can have a really identifiable reason why it shot up right there. That's the day we hired Bill. Then, okay, we need to work on Bill, get this thing back in control. Because if you don't do anything for Bill, it's going to stay up there for a while. It's not just random fluctuation. Okay, so let me move over to the WooStat server. And, well, actually, before I show SAS, I want to go back and pull up the PDF file and talk about this example. This is actually the 7th edition of the book, which I have a PDF file for. And yours is the 8th, but they use this exact example. I don't know if it's called 17.5 anymore. It may be 17.4 or 8 or whatever. But monitoring the water resistance of fabric, right? So this is outdoor sportswear, and you know what Gore-Tex is? Some of you nodded. Do you know what Gore-Tex is? You're an athlete, you don't know what Gore-Tex is?
Yeah.
Well, you're an indoor athlete, though. Gore-Tex is, oh, there's even a picture. Gore-Tex is supposed to be waterproof, right? So it's a raincoat, but it's breathable. So it has tiny little holes in it, but the holes are too big for water that's in liquid form to go through the holes.
It should be small.
What did I say?
Too big.
Too big? Yeah, too small for water molecules to go through, but water vapor molecules can go through. So when you're sweating inside there, your sweat can vaporize and go out, but rain can't get in. Right? So that's Gore-Tex fabric. Well, one of the ways they test it is for waterproofness is they push water against a sample of the fabric and see how much pressure does it take before they can actually force water molecules through the fabric. Right? So that's called water resistance. So that's what this is all about. So we got water resistance. It says for one particular jacket, the manufacturing process has been stable with a mean resistance of 2750 millimeters and pressures measured in millimeters of mercury. Have you heard of this before? Even blood pressure is measured in millimeters of mercury. And anyway, they have mercury in a tube, and right. So mercury is a heavy liquid, and whatever gets raised, it's like a thermometer or whatever. Anyway, that's not important to this. So that's just the units. So 2750 millimeters of mercury, and the standard deviation of the process is 430. So the mean is at 2750, but it has common variation on each side of that of 430. So an operator measures the resistance on a sample of 4 jackets each 4-hour shift. Right? So during each of the 4-hour shifts, they take one sample of 4 jackets. And then I'll show the table that he's talking about here in a second, and it says it gives the last 20 samples. So, and then from each of those 4 samples, they produce the mean and the standard deviation of the sample. And so instead of mu sigma, it's x bar and s. Okay, so let's look at those. This is a slow process. There's the chart. Okay, there it is. So this is 20 control chart samples. Right? So each sample has 4 measurements, and then they compute the sample mean of that and the sample standard deviation of that sample. So if you just plugged into a list in your calculator, these top 4 numbers, you'd get a mean of 2534 and a standard deviation of 218. Okay? Then each of these sample means can then be plotted on a chart. So if we do that, it looks like this. So let's look at this. I didn't turn on my marker, so let me see if I can figure out how to do that. You guys have taught me enough times, maybe I can remember. Okay, so where is this line drawn? Do you remember the number? What'd you say? 2750. Right, that was mu. Right? You remember what the sigma was? 430. So mu plus 3 times and what was our n? No, there's 20 different means, but each of them came from a sample of 4. So it's over 4. Right? So plug in 2700 there and get your calculator and actually compute that for me. 2750 plus 3 times 430 divided by square root of 4. I'll do that for you in my head. Square root of 4 is 2. So you could actually divide that in and simplify your arithmetic a little bit. You got it, Brant?
Yep.
What is it?
3,395.
What?
3,395.
3395. Okay? So if you look at where this dotted line is, that's at that point. All right, so just a little under 3,500. Here's 3,000, there's 3,500, so 3,400 basically is 4/5 of the way up. Right? And then now do second function enter on your calculator, pull up that and change the plus to a minus. You'll get this lower one, which looks like it's at about 2,100. So what is the number exactly?
2105.
2105. Okay? So then they repeated this for every 4-hour shift for 24-hour shifts in a row. And they plotted those X bars that were on that previous table. So you see it's randomly staying around the mean and within control. It's staying between the dotted lines. Yes?
What if you have a lot of variability within your sample of fluid?
Um,
How do you catch that?
That's a great question. And that's the next topic. That's called an S chart. This is an X bar chart. I don't want an equal sign. X bar chart. Right? So it's almost like I paid him to ask that question right then. What if your standard deviation inside your 4, within your sample of 4 is changing over time? That's called an S chart. So that's a standard deviation chart. Right? So we'll do a very similar thing for standard deviation charts that we did for mean charts. They're a little more complicated, which we'll get into. You got a question?
Okay. Remember when before we used to do this, and most of them over the top of the bar and most of them over the bottom of the bar were kind of mostly equal. In this one, it's heavily skewed towards the bottom. So either we're looking at something that is behaving as it's expected, or we're looking at something that's heavily skewed towards the lower end of the scale versus the upper end of the scale.
Good insight. Very good insight. That's section 17.3, I think, and it's called the runs test. Right? And so, even though you're within the limits, if you notice that, it seems like most of them are below the mean. Right? So I would agree. If you count these dots, there's 20 dots total. 1, 2, 3, 4, 5, 6, 7, 8 of them are above the mean, which means 12 of them are below the mean. And hey, it seems like most of them are below the mean. So you count, well, how many in a row do you get below the mean? And if you get, and usually the number is 9. So this is in a later section. We'll talk about where that comes from. But here I got 1, 2, 3, 4, 5, 6, and then it went above the mean. If I had stayed down for just 3 more, then even though it's within the limit, you would send off an alarm and go, hey, it looks to me like you're below what the target is. Even though the variability is pretty good, you don't have the pressure that you're supposed to have. Right? So in a control chart like this, you don't flag anything until a point actually goes out. So if this one had been up a little bit and it went like that, then you put an X on it right there and go, hey, that one's out of whack.
Who cares? It's performing above.
What's that?
Who cares? It's performing way above what it should.
Well, that's a good point. That he said, I don't know if you could hear it on the video, but he said, well, who cares if it's out in the up direction because the pressure's better, right? The pressure's better. Well, maybe if it takes too much pressure, maybe water vapor can't get back through. Maybe that would be a problem. I don't know. Making that up. But also, maybe it costs more to have fabric like that, so you're spending more than you need to. This is plenty to keep rain out, so if you're doing more than you need, that's just costing you profit. It could be. So from the customer's perspective, hey, fantastic. But possibly from the manufacturer's process or perspective, you wouldn't want that. Okay? So now let's talk about S charts. S charts are trickier. So let's see. I want to go. Oops. Not what I wanted to do. Oh, I got to turn this on. That's it. Now you, at this stage of your statistical career, you may not have had too much discussion about sampling distributions of standard deviations. We talk ad nauseum about them for means, right? The central limit theorem tells us it'll be approximately normal, blah, blah, blah. Well, the sampling distribution of sample standard deviations isn't normally distributed. And so there's bias involved with that. The mean of standard deviations, and I could show you this on my pulse data that I collect from my MA343 students, right? If I look at the standard deviation across every class from every semester through 13 years of data collection, and I take the mean of all of the standard deviations, it will not equal the standard deviation of the whole population. It won't equal sigma, right? So the mean of all the standard deviations is not equal to sigma. It's a biased estimate. And that's a problem. So to correct that bias, there is a correction factor. And just from convention, and that's about all our author tells us of why the subscript is a 4 on that. By convention, they use a 4 for this one, and there's a couple more that we'll deal with. The sigma of the sigmas is also not equal to sigma. Now you think, well, the variation in the sample variations, that amount of variability should be the population variability, but it's not either. So sigma sub s is a different correction factor times the population standard deviation. Now remember, this sigma is assumed at this point to be known. You've been monitoring the process for long enough, you've got a lot of data, you assume that sigma is known. Right? So for our S chart, we need to know, where do I draw my center line? Well, it's going to be a function of the population mean, but it isn't going to be, not population mean, population standard deviation. But it isn't just drawn at the population standard deviation. Because the expected value of sample standard deviations isn't that. It's a correction factor. So the center line of the S chart is at C4 sigma, and then the upper limit is mu s plus 3 sigma s, which, okay, now do some algebra. Substitute in, and that's C4 sigma plus 3 C5 sigma. And you're thinking to yourself, ooh, algebra. What can I do with the sigmas? You can pull those out. So I have C4 plus 3 C5 times sigma. And if this C4 is a correction factor, and it's just a constant, it's a constant that depends on what size samples you're drawing. So I'll show you a table in a second. But it's just a constant, and C5 is a constant. This whole thing is just a constant. So somebody along the way said, well, let's just call that a new name for a constant, and they call that B6. So that's B6 times sigma. So that's all of that. And then the lower confidence limit is derived similarly, and I'll dispense with all the algebra, but they just call that one B5 sigma. Okay, now wait, here's my S chart, and it's the left edge of it. So my center line is drawn at C4 sigma. My lower limit is at B5 sigma, and my upper limit is at B6 sigma. This is a B, not a beta. I got a little tail on it there by accident. Okay? No, I'm out of time. So next time I'll pull up the PDF file, show you that table, and that table will be available for you when we take a test. So you can look up what values are for those constants. I actually wrote a SAS program to figure out where did those constants come from, and you can actually you can program it to come up with those. So it's fairly straightforward. It's all explain it if you're interested, but it's not something you'll have to be responsible to do. So we'll see you next time, and we'll continue on. We'll actually work with some data.